This is loud. I'm sure you can hear me in the back, right? Okay, let me keep on talking and see if we can tell. This is better. This is good. Okay, the other problem for those who are going to use this mic is that if you do it like that, nobody can hear you. So this mic is like you have to be drinking from it, otherwise then nobody can hear. It's very, very pointed, which is a bad idea for an auditorium. But, you know, as many of you know, we just moved to this building in September, and we're learning all about the things that we need to improve. So this guy over here, actually, Craig Hogan, is our checklist man. So if you find more comments for him to have in this long list of issues with the building, please send it to him. Or tell him on the break. But if you ignore the fact that the microphone is hard to speak to, it is a beautiful place, and I hope you enjoy our wonderful view of the courtyard, and we will go at the end of the day upstairs for the lounge where you can see downtown Chicago, and it's really, really wonderful. So we're very happy to be in this building, and we're starting this morning very early with the beginning of the universe, with the early universe, which is why we have to wake up early for that. If you sleep a lot, you miss the whole Big Bang. So, what we're doing today is celebrating 123 years of the Department of Astronomy and Astrophysics. I am Angela Lind, I'm chair of the department now. I am one of the many that followed our wonderful first astronomer at the University of Chicago, George Ellery Hale. We heard a wonderful story in the journey to Palomar. Those of you who couldn't come last night, do check it out. It's a wonderful documentary about his life. And today, the plan is to review everything that we've been doing in the department in very, very short time. So it's going to be very condensed, but with the goal of making predictions for 2042. 2042 is when we will celebrate 150th anniversary, our anniversary of 150 years. So we will put our predictions that we come up with today, and anything that you send to our website. We have a scrapbook you're all welcome to make comments and these predictions. We'll put this material in a time capsule to be opened when we do celebrate 150th anniversary. And then we will be amazed at the brilliance of our colleagues today that were right on the money on their prediction, or we will be laughing a lot, which would be fun too. So this is the goal. And we'll start with John and Shawen running. Where is she? Aren't you up here? Aren't you a co-organizer? Anyway, so co-organizers of this morning's session, which starts with cosmology, so the early universe. Thank you, John.
Thank you, Angela. I'm John Carlstrom, and Shawen and I are in charge of organizing the session on cosmology. Shawen will be here in a little bit. And we're going to start with a history of the department, a brief history that Josh Freeman is going to give. Josh is a professor here in the department and also a scientist at Fermilab, and also the director of the Dark Energy Survey, which you haven't heard about yet. People certainly will hear about in the future.
I think I can use this. Great. Okay. Well, it's a pleasure to be here at 8:30 in the morning. So like Scrooge, I'm just waking up, and so I'm going to be talking about the ghost of cosmology, past, present, and future at Chicago. So cosmology at Chicago, of course, started with Edwin Hubble, who invented the Hubble constant, the Hubble law, the Hubble diagram, and a whole bunch of other things, the Hubble Space Telescope, Hubble Middle School. And of course, he pretty much invented the field of observational cosmology and ushered in the long, glorious era of Chicago athletic prowess, and also was really invented branding in cosmology, and was very good at it. Something we're also, we still do today. So here's the 1909 track and field team. Can everyone figure out which one is Hubble?
The one with the pipe.
Yeah, the one with the pipe, yeah. Okay, thanks. So there's Hubble. So he clearly was a very, well, he was a good athlete. He was such a good athlete that he was also on the 1909 national champion basketball team at the University of Chicago. So I don't know when he had time to do any astronomy or anything like that, because he was clearly always and clearly a very happy-go-lucky kind of guy. So this basketball has come down to us through and is now here. And this is astronomer John Grunsfeld, a PhD from the University of Chicago, who took Hubble's basketball up onto this space station during one of the Hubble servicing missions. And here's the presentation he gave with our former chair, Rocky. And it's sort of interesting the way Rocky's looking at the basketball. And I think he's clearly thinking of stealing the ball from John and going in for a layup. So flash forward from Hubble to the early 1980s. Many of us were fortunate to know and work with and be mentored by David Schramm, who really was instrumental in really forming this whole field of early universe theory and particle cosmology, and formed the Fermi-Lab Astrophysics Center, mentored a number of people here in the audience, and continued Hubble's long tradition of combining cosmology with championship sports. He was actually a championship wrestler, also a very accomplished mountaineer, skier, bicyclist, racquetball player, etc. And David, I think, really had great foresight and realized that this whole area of early universe cosmology was going to explode, was going to expand, and really did much of the work and laid out much of this entire field, studying Big Bang nucleosynthesis, the origin of baryons, inflation and structure formation, the particle nature of dark matter, etc. And this concept of using astrophysics and cosmology as a laboratory to study elementary particles and vice versa. And of course, another thing that David did was he hired two young cosmology theorists to Chicago and Fermilab, Click and Clack, the Taffet brothers.
Hey Josh, which one's the macho and which one's the wimp?
Yeah. And I have to say, I searched all around the web. This is the best picture I could find of Rocky and Mike. And so they continued this tradition of, well, actually, we're not so good at branding, so we take credit, Mike, inventing nomenclature like WIMPs and dark energy, but, it's not Hubble WIMPs or, it should be Chicago WIMPs, I think it should be, Anyway, so here's all right, this is maybe a better picture of Mike and Rocky. For some reason, I think it was Rocky who sent us this picture. Right. Okay. So then moving forward to the 1990s, I think this was really the era of kind of the return of many of observational cosmology to Chicago. Don York, Rich Crone, Steve Kent, and others gave us this wonderful Sloan Digital Sky Survey. Here's Connie Rockesy, an alumnus, wearing her Chicago sweatshirt, driving the Sloan 2.5-meter telescope from her laptop. And eventually, I think they put in some real computers to drive the telescope, but this was in the early days, and it gave us beautiful maps of the large-scale structure of the universe. And here's Don now. We're continuing that tradition in great optical cosmology surveys with the dark energy survey. Here's the dark energy camera mounted on the prime focus of the Blanco telescope. And here's some of the people who've been directing that project over the years, including Rich and myself and John Peoples from Fairmont. The golden age of, we've really entered now a golden age of Chicago CMB experiments, and there's just, it's really remarkable, I think, just looking back over the last 20 years, the variety of experiments that have been carried out, led by a number of people here, John, Steve, Abby, many others. And here's the South Pole. This is actually a prototype of the South Pole telescope being tested on the Midway in January before it was deployed down to the pole, and it worked well. And of course, it's given us great results, and there's a great future here that we'll be hearing more about. I think the other thing that struck me in sort of looking back over the history of cosmology in Chicago is just how much it's grown and blossomed over the last 25 years or so. So we now have a whole cadre of really talented people doing cosmology theory. Some of them look younger here than they are in real life today. That's good. And of course, we've had this blossoming and burgeoning of observational cosmology as well, both optical, infrared, and particularly cosmic microwave background, far infrared. And this is really, all that's really happened in the last 20 years or so, and it's tremendous. Sorry? Of course, another really exciting thing has been that over the last 15 years, we've brought theory and observation at Chicago together under the umbrella of what's now the Copley Institute for Cosmological Physics. Here's a subset of people associated with the KICP, and we really, of course, have to thank and remember the vision of Bruce Winstein for putting this all together. So I think, the message here is that the cosmology present at Chicago is really strong and really thriving, and it's great. I want to spend the last couple of minutes of my time looking forward to the future, and you'll be hearing more from other people looking forward. So we were told to look forward to cosmology in 2042, so when the university will be celebrating its 150th anniversary. And so I've made a number of predictions of what cosmology at Chicago will look like in 2042. So that year we'll have first light for GMT, so that'll be great. It'll be really exciting. Of course, it will have been reconstructed after that magnitude 9 earthquake in Chile. JWST launches in 2042, that's great, very exciting. Lots of, and it'll be really synergizing with GMT on the ground, it'll be great. We'll be only 2 years from the launch of W1st, which will be open up and again be complementary to the near-infrared surveys of the universe. That will be the year that LSST will decidedly confirm the discovery from the dark energy survey that the equation of state of dark energy is less than -1. We live in a phantom universe. CMB S8, so as you know, we're now heading towards CMB S4, so in 2042, CMB stage 8 will have improved the constraint on the tensor to scalar ratio to less than 10 to -6. And so we will be hosting the Cyclic Universe 42 conference here at Chicago, one in a long series. The 10th generation dark matter experiments will be underway. The detector will not be the size of Rhode Island, the detector will be Rhode Island, in the hopes of finally discovering weakly interacting dark matter. The next generation holometer experiment will in fact discover that it's turtles all the way down to the Planck scale. So we'll finally understand the structure of space-time. LHC will be celebrating the 30th anniversary of the discovery of the Higgs and the 10th anniversary of the discovery of extra dimensions, but still no supersymmetry. We will just have have been awarded the 10th PFC for the Physics Frontier Center for the KICP, which will be titled Pushing Cosmology Way Over the Edge. So 2 years earlier, Astro 2040 will have finally recommended construction of the square kilometer array. And so we will be giving serious consideration to moving into the field of 21 centimeter observations here at Chicago. Sorry, that's an in-joke. We'll be starting to teach astrobotany classes at the Chicago Mars campus, which is, anyway, that one you understand. Yeah, right. And also, at that time, the astronomy department at KSCP will all fit into a broom closet on the 5th floor. That would be the last unused space by the Institute for Molecular Engineering in this building. So we'll be hoping for a new building by then. This will be a midterm election year, and so President Malia Obama may suffer some setbacks in her party at that time. I just have a couple more. First of all, climate change will have changed the nature of astronomy being done at the South Pole. So it's going to cause some mount problems for SPT 9G. But unfortunately, it's going to make it much easier for graduate students to access the photomultiplier tubes for IceCube. So that's what's being contemplated here. Okay, my final prediction. So here we are today. November 18th, 2015, at 8:30 in the morning. My last prediction is that when we come back in 2042, the cosmologists will have enough oomph that we'll be able to start at 9:30 instead of 8:30 in the morning. Okay, so that's all I have to say, and I'm going to turn it back over to Joanne.
Thank you, Josh. And you can ask Josh questions later, explain some of those predictions. So we're going to try something a little different for the rest of this session. So we're going to have a panel. Oh, there we go. We're going to have a panel come up, and I want to introduce the panel members. Abby Barrett, who is an Associate Assistant Professor in the Physics Department. She works both in the Antarctic and the Arctic, doing everything from cosmic microwave background to high-energy neutrinos. Xiaowen Chen, who is an associate professor in the astronomy department, who has studied galactic evolution and the processes which lead to star formation, the evolution of galaxies. Josh Freeman, who you just heard from. Wendy Friedman, who is an observer, new professor in the department. She's actually the John and Marion Sullivan University professor, a key observer determining the Hubble constant, and Craig Hogan, who is a theorist, here a professor at Chicago, and also at Fermilab and Mons, the Center for Particle Astrophysics at Fermilab. So what we've done is we've written to the alumni and gotten predictions or statements or questions for the panel from alumni. And we're going to go through some of those. And before we do that, we're going to have actually Xiaowen just give a brief introduction to what's happening with telescopes here. Kind of a new initiative, or a rebirth of telescopes here at Chicago. And as Xiaowen likes to say, we put physics and astrophysics at Chicago. So Xiaowen, work the slide.
All right, thank you. Good morning, everybody. Many thanks to Josh for, I maybe want to step
You have
back.
to hold that right up.
Okay, not quite there yet.
Unfortunately, we're just hold it. Yeah.
Yeah, so I thought to transition from Josh's very nice introduction and overview of the history, I would just add a bit of my own perspective about this department. Since the celebration started last night, we've seen Journey to Palma, a very inspiring historic review of how the department started and following Hale's footsteps to the pursuit of giant telescope. And also, given my own, given the history of how cosmology theory and experiments started in this department, I thought one thing I found a common theme among this, which is a unique feature of our department from the very beginning, is this is really where physics meet astronomy. And that's really ingrained in our own, in the name of the department, where the Department of Astronomy and Astrophysics. And also, this is also where theory meets observations and experiments. I thought this is one thing that made us, that carried us to where we are today, being really successful, being always out there, doing cutting edge and leading the field development. And if I have to make any prediction, I would say if we continue this methodology, this culture, I'm pretty sure we'll still be at the leadership position 27 years from now when we celebrate the 150 years anniversary of the department. But given my own research interest is in doing observational astronomy, and I thought we should, in order to really make educated guess for what's going to happen in 30 years of time, a good way is to look back how the history has evolved. Specifically is in how, in the pursuit of the giant telescope. So what you're going to see here is the, what I characterize as the race to the most powerful time machine, starting from the beginning where Yerkes started in 1893. That's marked by the red tick mark here. And then we are here in 2015, and this is our task, predicting what's going to happen in 2042. So you can see, this is certainly not a complete list, but the major facilities are all included here. Starting from Yerkes, it took us over 50 years to reach the 200-inch Palomar telescope. And after that, you can see in 1970, there's the boom of a suite of smaller telescopes in Chile and also in the United States. Come after the 1990s, I feel lucky that this is my generation. You can see a bunch of 8 meters, 10 meter class telescopes coming online in conjunction with the Space Telescope. Also adding to that, this is the Sloan Digital Sky Survey, initiated, launched by our own colleagues here in Chicago, that completely transformed the field. So now we are, as you saw and heard last night, that we are, the whole world is in the whole race to reach the next largest telescope on the ground. That includes GMT, TMT, and ELT, with an expected first light somewhere in 2020, 2025. So once, between now and then, we would have been carrying the ball out of Hubble's playing field. This is the true to scale basketball court size. We will be officially exceeding the size of the where Hubble played. So I thought that was really, really amazing. The kind of speed we are going forward. And as an observer, an empirical observer, what I would do is, looking at this trend, I would just try to fit a curve, how the time evolved. So this is linear in time and linear in aperture size. You can see this is a very steep uprising curve. Even before 2042, we might be diverging to infinity. So what's next? Square kilometer arrays. This is probably not a fair comparison because that will be in radio, but who knows, maybe all observers will be shifting to doing radio experiments. Or next will be possibly going to the moon. Maybe we could build a radio array on the backside of the moon, or a liquid mirror telescope. As crazy as my song. But in any case, coming back to, I guess it doesn't matter where we are. I think this quote from Hubble from 1936, I found really, this is one of my favorites, where he said in this lecture of the realm of nebulas, we know our immediate neighborhood rather intimately. I guess immediate is the relative word here, going from the solar neighborhood now to perhaps Richard beyond 10, 12. But with increasing distance, our knowledge fades, and fades rapidly. So I think that's true always. And the search will continue not until the empirical resources, whatever that means, are exhausted, need we pass on to the dreaming realms of speculation. So with that, I'll pass this back to John and the panel.
Okay, thank you. Well, with that in mind, I want to go to some of the quotes that we received from alumni about cosmology in 2042. So I'm going to start with one here. This is Phil Coulter, 2001 PhD. That is an interesting time frame forward. Imagine asking that same question in 1988. No COBE, CFD, no dark energy, barely any galaxy clustering studies, no IRAS galaxy clustering, CFA2 just finished. the wild frontier of inflation models and early universe particle physics that are now basically all ruled out. So where will we be? No idea. That theme continues with our own Wayne Hu. That's too far from now, and then it did send me a quote, good theorists don't know what they'll be doing 3 years from now, let alone 30. Of course, what Wayne is paraphrasing is really this. It's tough to make predictions, especially about the future, and I couldn't find, Andrew maybe because I couldn't find when he got his PhD. We asked in the state of cosmology, Mark Kamiankowski told us he knew. He said the state of cosmology will be Illinois, just as it is now. Going further, Andre added that language we'll be using in 2042 to describe the universe and its cosmology will likely be qualitatively different from what we use now. I don't have a clue what that language will be, however. So for the panel, that's what I'm wondering about. We don't even know what language we will be speaking. And so I want to ask, I'll start with Craig, if you look back 25 years ago, predictions and what we're doing now, is it really that different? I mean, were they that far off? Is it hopeless? And I want to point out that 25 years ago, we were going to build a new astronomy building, and here we are, so.
It takes longer to tell a story. So I think Gil had it actually exactly right. That sort of 25 years ago, 1990, it's not that people hadn't thought about what we imagine now. It's that there was just so many other ideas out there that hadn't been ruled out yet. That you had all these crazy things. The people like Jerry Nelson, right? I don't know if Jerry said anything.
Can we get Jerry? Yeah.
Yeah, so in the 1990s, Jerry was running papers about making galaxies out of exploding stars, and, had nothing to do with the early universe whatsoever. And we didn't know that the radiation was thermal and primary fluctuation sediment. On the other hand, all the ideas we're using now were in place. When we had inflation, we knew about variant acoustic oscillations. So it's more like a winnowing effect that's happening. So I don't know what that means about the future. If you're looking to 20, we've already done the winnowing. So I think it's up to the experiments to drive it forward. I mean, I think you can't count on theory until we go back actually.
Let's go a little further, both from this thing. So here we are, Mark again. B modes. B modes will be mapped in the CMB, and we will find that Stephen Hawking's initials are written in the temperature map. I think we already found that. Bohl's rule will be written in the B modes. Finally, that's what the B and B modes do. It says, the landscape scenario, which we'll hear about a little bit later, will be pushing up daisies. Then he gets a little more serious. This is what we're up to. We are going to see in 2042 W, this equation of state is -1. That's Einstein's cosmological constant, dark energy. No B modes. NF, which has to do with the number of neutrinos, is exactly as predicted. No new physics at accelerators beyond the standard model. Is this going to come true? No new physics beyond what we see now. It's a possibility of the one that I don't hope for. What else would this whole cosmological problem verify in that case? And here's one from Asante Kure, 2001. Thanks to Euclid, this is now 2042. Thanks to Euclid, W first and LSST. It's a little more optimistic than Josh. We will confirm W equals -1 with some high precision, but that wouldn't say anything about what dark energy is. So we'll be designing experiments to look for another orders of magnitude and precision. In parallel, we'll be looking for experiments capable of detecting 10 to -5 departures from curvature. The curvature of the universe is remarkably flat. So we still won't be solving the dark energy problem, another kind of pessimist view. Here's a Dragon Murderer, 2000, oops, I think he was 2001 or 3. There's still no appealing, convincing, consistent theory for dark energy in the accelerating universe, leading cosmologists to increasingly rely on astrophysical observations for guidance as to the nature of both dark components. Current data, including that from WFIRST, which has just launched in the 2030s. So, what they're saying is that we've winnowed down so far that we have the model, right? This Landesian model, and we're just going after picking the edges, but we're not going to break. And so, maybe Wendy, maybe you could tell people a little bit about the model and where we are, and whether or not that pessimism is warranted.
So, right now we have in cosmology. That's all right. Okay. is what has been termed the standard model. And the standard today, as opposed to 25 years ago, when there was no dark energy, has the dominant component of the universe being in this form of dark energy, which we don't understand. And about 30% of the composition of the universe is in matter, with a ratio of about 6 to 1 in dark to ordinary matter, the stuff that we're made of. And it has a Hubble constant of about 70 kilometers per second per megaparsec that corresponds to an age of the universe of something like 13.7 or 13.8 billion years. And it fits in with a standard model grounded in general relativity and has an early epoch of inflation, an epoch when the universe was expanding exponentially, and led to a universe that we see today, a Big Bang universe, which we see the evidence for today in the microwave background and isotropic in all directions. And so, you asked me about whether we had reasons to be skeptical about the model?
Well, so we have this model. It fits all the observations, that's what you're saying. And it's made 96% of it is stuff we don't really know anything about, except that it's needed to make the model work. So it seems a little pessimistic to think we're done. That in 25 years we're not going to make progress on that.
Yeah, so I, for one, would be skeptical about the idea that we're done, especially given this period of how many things we threw over the side. And we thought in the 1980s that omega matter, the amount of matter in the universe, was maybe 20% of the critical density that is the divide between an expanding and contracting universe. And if only observers could go out and find the rest, then we would be done. There was, if you talked about the cosmological constant, which Einstein had put into his equation of general relativity to force the universe to be static, then, as the director where I worked at the time said, you'd have to be nuts to think about something like that and go do something else. The Hubble constant has to be 50, and we knew what the standard cosmological model was. So I think we reached a point where we didn't understand all of the data. Maybe dark energy is the answer. Maybe there is an equation of state for dark energy that's consistent with Hubble, with Einstein's cosmological constant, but maybe not. And I think I agree with Craig, this is going to come from observations. And I hope we don't have the full picture yet.
Well, our alumni get more optimistic as we go on. So here's some Coué, future version of CMB full polarization with cosmological background. We'll measure the amplitude of temperatures by 2040 to see a CMB B mode, clean from anything. But we still will be arguing about the physics of inflation. And here's Eduardo Rosa, that's 6. Will inflation ultimately lead to a new fine-tuning problem? I can imagine a world where we have 4 sigma evidence that our measurement detection of these B modes. But it's too small to agree with simple signal field models. Where do we go from there? And then he goes on to predict. I predict we will have an R greater than 0 detection, because why not? Which will lead us to fly ELISA, this solar system size gravity-based detector learned by inflation.
Actually, ELISA is the little one.
That's
the cheap one. You mean super duper.
Yeah, super duper. 24, super duper. I'll story, a recent graduate, the scalar to tensor ratio, detection of B modes, will have been limited to measurably small values, and we won't care anymore. But that'll be okay, because we will have figured out that inflation is not actually due to a new scalar field, but instead due to the quantum nature of gravity, ways to test the new theory. So let's start with Abby. Abby, what are these B modes, and why are they so important?
So the B modes that all these people were talking about are B modes from inflation. So what this is we have this theory of inflation that the universe expanded exponentially fast in the first tiny fraction of a second. And one of the ways to look for evidence of inflation is to look for a specific pattern in the polarization of the cosmic microwave background. So that's the B modes they're talking about. And of course, if we found B modes from inflation, it would be really, really interesting. And so the big question is that going to happen in the next 25 years? And I actually tend to agree with Kyle that we'll either have found it by then, or we won't really be looking for B-modes from inflation anymore. Because the experiments get harder and harder as you start to place tighter and tighter constraints on R. And I think, in 25 years, it's possible that we will hit the point of diminishing returns, where it gets harder and harder to, someone alluded to this as well, it gets harder and harder to remove the other signals, like from lensing. And it will hit this point of diminishing returns, and so the question is, maybe we'll have seen B-modes from inflation by then, in which case we'll be still measuring B-modes, as many modes as we can across the sky with the best sensitivity we can, and we'll be making fantastic measurements to try to figure out the physics of inflation, or we will have set some limit and decide whether to move forward or not.
Go on a little bit. On that vein, the rights, the phrase quantum cosmology will actually mean something. And it will be theoretical, observational, and experimental. Tom Crawford asked the same thing. Between now and 2042, we will have a breakthrough on the theory side that explains, ties together dark energy and inflation. Could be a viable theory of quantum gravity, could be something utterly unexpected, but as soon as it's written down, someone will say, oh, that's what we were missing. And it will be aesthetically pleasing, most importantly, and in no way involve anthropic reason. And then our Greg Hogan here has added, we have a quantum theory of gravity that will explain the origin and exact value of the cosmological constant and its relationship to a new and deeper standard model of matter and forces. The theory will agree to set precise laboratory experimental results for many significant figures. So Craig, what will this theory look like? And when someone stumbles across it, will they say, that's what's missing, or like Alan Guth, right, or Eureka in their notebook?
Which president was the one that had a secret plan in the war? I have the theory in my bottom drawer. I'm just not sharing it with you.
So it was Jerry.
No, I mean, of course, I don't have an answer, but I think the message here is that if you want to look outside standard theory, you have to look outside standard theory. You have to look outside. It's not going to be field theory. It's not going to be GR. It'll be something that reduces to those two things in appropriate limits, but makes new predictions that we can test. And I think it's not crazy. We'll talk about this later in the particle astro session. It's not crazy to imagine an explanation like that. We can connect the standard model with quantum gravity and get something like a cosmological constant out.
So the answer may lay in what we do here, which is bringing all these things together. Okay, here's another one. There will be several determinations of, separately, the primordial helium abundance and the Hubble constant. I mentioned separately because actually the cosmological model, they become involved. None of which agree with their stated error bars. So Wendy, you're measuring the Hubble constant. What do you think of that prediction for 25 years from now?
I agree. But the error bars will be smaller, and if we don't have disagreement, we're not pushing things hard enough. But I think they'll be less than 1%, and I won't be interested in it anymore.
So the error bars, people overstate their error bars and missing systematics, but they'll be getting the right answer. There's no tension, there's no
I think
clue to something else by them not agreeing.
so. It's a question of how far down you have to push things,
Yeah,
and I
how
would
far
say
down.
if we can get to 1%, which I'm not going to minimize the challenge, and it might not be 2042, then it won't be interesting. But I think we didn't think it would be interesting less than 10%, and it's much more interesting now. So.
But now that it's a few percent, aren't we still about the same error as between predictions?
Yeah, I think the nature of the measurements is that systematic errors dominate, and it's usually unknowns that are the culprit, and until you get many independent experiments and each of them push down the systematics to the level that they can, then you begin to find something more interesting. And I think that will continue to be the case. Systematics will dominate, but the error bar, the uncertainties of measurements will get smaller.
Those new telescopes show us points. We'll get there. All right. Okay, here's a Eduardo. Ooh, just to be contrarian, cosmology manages to put an upper limit on the neutrino mass that is in violation of the neutrino oscillation theorem. What's the solution? Or as Abby said, precision measurements of anomalies seen in the reactor neutrino and accelerator neutrino experiments confirm the existence of stereo neutrinos suggested by measurements of some neutrino masses from cosmology that are in conflict with the known mass differences from accelerator, reactor, solar experiments. And Asanta on neutrinos. Euclid, here's a very optimistic one. Euclid, W first, L says T, CMPS4, etc. will all be successful. Well, of course, Chicago experiments. And cosmology will measure the sum of the neutrino masses and neutrino hierarchy. Some members of the audience will have received the next Nobel Prize for neutrinos, for exactly that. The 2040s neutrino community will be looking for its next science goal, a clever experiment with a technology breakthrough to directly detect the 1.95 cosmic neutrino background. And for those of you who know about the cosmic microwave background, remember for every cosmic microwave there's another neutrino almost whizzing through you, going through the Earth, everything, trillions per second going through, and we don't know how to detect it. But Abby said that we will know how to detect it. Cosmic neutrino background. After this cosmic neutrino background is discovered, we figure out how to build a directional, not just detect, but map it, directional tritium endpoint detector with a volume big enough to see tiny fluctuations and make maps. So there's a bold one. So, yeah, Abby, how, you want to say a few words on how that works? This sounds very exciting.
Yeah, it's sitting in my bottom drawer.
In the
Yeah,
bottom lab.
So the ways that people have proposed recently to try to measure the cosmic neutrino background, and if you could do it, it would be amazing, right? The way people have proposed is by building a big vat of tritium and looking for electrons, a bump in electrons that's caused by neutrino capture on tritium right near the endpoint of beta decay.
As big as Rhode Island.
Energy.
Yeah, the energy endpoint. Yeah. And so, the currently proposed experiments already use a ton of tritium, and in order to see, I don't know if that's a qualitative statement, a lot of tritium. So the question is, when I sit back and dream about what you could think about building in the future, I sit back and dream about building a cosmic neutrino background experiment that would be able to see anisotropes. And how would you do that? I have no idea. But if you could figure out how to build a directional version of that detector that was, 10 to the 4 times bigger, you'd be doing pretty well.
Okay. So that's pretty cool. We're going to detect the neutrino background, and then we're going to map it. But our alumni are thinking even bolder. Lloyd Knox is saying, we will detect it, but he wants to actually map it, and not just on the sky, but in energy. And he points out this cool thing, which he introduced to Scott Wilson. So in 2006, he said, so he's an overachiever. He writes a lot too, you can see. We will have a map of the cosmic neutrino anisotropes at a range of energy. So not just the mapping of getting its energy spectrum. Scott Wilson was the first to point out to me that due to their non-relativistic speeds today, these neutrinos are actually arriving here from close. In other words, they're not traveling at speed of light, they're traveling a little slower. So occasionally we see a different surface than last scattering, which is kind of cool. Then he goes further to add to the coolness. Because neutrinos have mass, their time of flight from scattering now depends on their energy. Right? Higher energy moving faster. And so it means by mapping out the cosmic neutrino anisotropes at a range of neutrino energies, we can sample the multiple last scattering surfaces. So that's one thing that will be happening when I'm 99 years old, and you can't wait to read about it. I think you should be patient. But Gil goes, which he also goes on, we have measured fluctuations, this is in 2042, we have measured fluctuations in cosmic neutrino background with different energies corresponding to different distances from us, as we just explained, and a different amount of gravitational cleansing, allowing a full 3D map of the real initial conditions of our Hubble body. So I'm going to ask Josh. Josh, do you think this is where the field is headed? This is terribly exciting. But aren't there other ways also to measure the 3D map, galaxy surveys, and just, what do you think?
Yeah. Well, I think Yeah, I mean, I think by 2042, galaxy surveys are going to be passe. We'll have measured, redshift spectra images in multiple wavelengths for billions of galaxies. And yeah, I think
Billions and billions,
yeah. I mean, I think one thing that I'm struck by, sort of looking at the history of the last 25 years, is every time there's been a new opening, a new observational window to the universe, we've been extremely lucky. So I remember sitting in a conference with Paul Steinhardt in 1994. We were talking about the future of CMB, but then we had COBE. COBE sort of looked vaguely like what we expected it to look like. But at that time, people were planning to try to get to smaller scales, look for the peaks in the power spectrum. And you look today at the power spectrum, the temperature, the polarization from SPT, from Planck, and the fact that it looks exactly like what we expected is remarkable. And the fact that it looks anything like what we expected, instead of just a bunch of mishmash gobbledygook that we have no way of understanding, that to me is really striking. So in some sense, I'd say we've been so far much luckier than we had any right to believe that we would be. And we're now in this precision era. We're trying to get things down to percent level or less. We should remind ourselves that there was no real basis for optimism that it would turn out that way. So yes, I think to go beyond where we are now, we're going to need new tools, like the neutrino background, other things. I think what we're doing currently with CMB measurements, galaxy surveys, it's fantastic. It's going to be great for the next 20 years, but at a certain point, we're going to hit a wall there. We're going to need new tools.
So, new tools. Here's another potentially new tool, which Josh said we'll be discussing in 2042 if we're interested. But Abby wrote, we'll have a detailed 3D map of the history of most of the first billion years. I wasn't sure if it meant the first or last. Depends on that. Using 21 centimeters, using the transition of atomic hydrogen, spin flip transition. We'll still be talking about going back to the backside of the moon to get away from radio noise. Do you want to say a little bit where you think 21 centimeters is headed?
Yeah, I mean, I think 21 centimeter is a really promising experimental field, and in order to build an experiment that could do something like make maps in the hundreds of megahertz range, you have to build quite a big experiment. And so this is sort of part of the promise of SKA. People are also talking about, eventually you'll hit, and it's a big problem with 21 centimeters, how do you get rid of not only man-made noise, but also foregrounds. And so in order to get far in this field, you're going to have to think hard about that. So I don't know what the answer is. But I do think, it would be a fantastic wealth of information if you could do it.
One of these new windows.
Yeah.
So this is Daisuke. You wrote a lot. I tell you what he's saying is galaxy cluster cosmology will deliver. We'll understand the gas dynamics, astrophysics, we're going to understand the mass, we're really going to understand and use these to do cosmology. So I wonder if Xiaowen might comment on this, but also comment on why stop at galaxy clusters, galaxy evolution, structure of galaxy, that's also. Where do you think that's all headed?
Well, that is my dream. That's what I keep pushing our theorists, colleagues, to come up with a way so we can actually push down the mass scale, not just stopping at cluster scale, but moving into group, even individual galaxy range. I'm hoping that very soon we will be there to use many more orders of magnitude more galaxies to help constrain cosmology.
The GMT is going to do that, allow that.
For sure.
So here's a cost-saving idea from Scott. We will be able to give a computer a map of the cosmic microwave background, have to spit out cosmological parameters, which I assume is also tested on, without us telling it what we think we know about cosmology. Wow, what a cost saver to NSF grants. we just have this computer program take the observations. But Josh, are we headed there? And should Scott just be talking about the CMB, or is that where simulations and everything of galaxy cluster surveys or 21 San Francisco where we're headed?
I thought we were already there, no? Isn't
Is that where we are already?
Don't you just feed it to a computer program and it spits out the cosmological zones? So yeah, I think
Notice telling them what the model is.
yeah. Yeah. No,
And then computers
that's
do
what-
the observations while they're at it?
Oh, eventually, yeah. Eventually it'll be all robotic, right? All observational astronomy will be done by robots. Yeah. We'll have robot donors, and it'll be we'll be sidelined.
Fantasy astronomy.
Yes, right, and it'll be legal. Yeah, I think part of what Scott's highlighting is, and something that we haven't talked about, is, you know, with the increase in the telescope aperture, with the increase of, the other thing that's been very dramatic in observational cosmology over the last 20, 30 years is not just, we're sort of at the beginning of the large growth in aperture. We've been in a large growth of detectors. If you look at the number of CCD pixels on the sky, that's been growing, you know, at Moore's law rate for a long time. If you look at the number of detectors you have in CMB experiments and other experiments, you know, that's growing enormously, 21 centimeter, and it's becoming a huge computational challenge just to analyze those data. That's happening with galaxy surveys as well. And we've been lucky again so far that sort of the Moore's law rate of computational power has been more or less tracking the needs that we have for analyzing these increasing data sets. Whether that's going to continue in the future is not yet clear. At some point, you know, having very large computer clusters is going to take, you know, the power that's now delivered to the city of Chicago to power and cool them. And so we're going to have to find perhaps some other technological ways of having computing power keep up with the needs. But again, you know, we've been lucky so far that the computational technology has been sort of matching the growth in detectors.
So this is a very big problem for the LHC.
Yeah.
Unsolved there, that's for sure.
Go on. All right, so let's drag out again. Now that it's 2042, we are celebrating 50 years of since COBE, 30 years since Planck, 10 years of CMB S5, and they discovered, in order, primordial density fluctuations in CMB, Nobel Prize was given out for that, large angle anomalies in the CMB, which people know about, we don't know what to think about that, and the signature single horizon size cosmic string cutting across anisotropy pattern. You know, new surprises, this is awesome. What are they? And I actually have a question, I'll direct this at Craig, but for anyone. Are these large-scale anomalies, are those going to be something that go down as a discovery, or something that gets finally, that's just unlucky?
Yeah, they'll fade away. So I did want to, so it's the thing I haven't heard about yet, I don't know if you have a plan for it, is standard sirens. Do we have anything?
No, I thought that didn't happen, but please talk about it.
Well, I mean, I think it should be mentioned in this session, because, I mean, it'll be a critical tool for cosmology in 2042. I mean, that's just a prediction I'll make right now. Well, not only will we be detecting gravitational wave sources, but they'll be used as a precision tool for distances, and it'll, you know, it's right now those fields are so separate, they're morning and afternoon sessions. 2042, it'll be the same session. Yeah.
Okay, any other comments on discoveries? I mean, my feeling is we've been driven by discoveries.
Yeah.
We had those models, which are a little bit more again at the end, but the discoveries are driving it.
Yeah,
I'm sure we got the
and
right
because
model.
of that, there's this constant hope that this one's real. You know, this time it's really a
This
surprise.
time we
It's
got
gonna
it
stick.
right. Yeah, we're done now.
But the pattern has been, as you know, right, that you know, they basically gone away. We converged on the simplest model, just extraordinary. The universe is so simple,
Aside
fairly.
from Mendes was
No, Lambda was written in 1919, right? That's Einstein's. So far, it's consistent with.
That it was going to go
It
away.
pretty much
That was
died.
a fashion. Again, no, I mean, Eddington thought it was there. I mean, that was Whipsaw's of observation.
Okay, let's come back to that. Hold that thought. We have a couple more. We might even have time for questions. CMB spectral distortions. So this is not the mapping, but the spectrum. After the first successful CMB spectral distortions mission, we'll build an experiment that can characterize mu and y distortions from the early universe. And let me go on. This is CMB, and then we'll ask Ed to talk a little bit. This is a bit long, but this is John Kovac. 25 years ago today, I was at the South Pole my first trip. Grad school was still 7 years in the future. The CMB was still isotropic, but expected to be done in 5 years or so. There was no lambda yet, except possibly after my term. Today, it's at the South Pole, actually right now, at the damn South Pole. CMB drives precision cosmology, but it's expected to be done 5 years ago. The data loves this model. 25 years from today, no idea where I'll be. Whatever the physics that CMB was teaching us will be expected to be done in 5 years or so. Lambda CDM, this model will break at some point. I hope my turn will have a great name for it. So CMB, it seems to be the gift that keeps on giving. You're not talking about spectral distortions. Is it job security? I mean, will we finally exhaust all the information CMB has? Will that happen in 25 years?
Well, it hasn't happened yet. As John Kovac said, it keeps seeming like it's 5 years around the corner, but it hasn't died yet. I will make one prediction that John Kovac will be at the South Pole again in 25 years. That seems to be one trend. But I do think there is information still to be harvested from the CMB. Some people earlier talked about B modes, and that'll go on for the next at least 20 years. But I think it's possible that in 25 years, the search for inflationary B modes, if we discover them, we'll still be making precision measurements. But if we don't, it'll be harder and harder. But one thing that people have talked more and more about recently is CMB spectral distortions. So this is measuring the frequency spectrum, not the anisotropies of the CMB, to try to learn about, a variety of things. There's a variety of things that would make the spectrum not exactly black body. But we can hope to learn some more about the physics of the early universe from that.
All right, going on, here's Jerry Ostreicher, esteemed alumni. We will know what most of the dark matter is. In fact, I know already, but not telling. We will have a physical model for the dark energy and some testable predictions. We will have a replacement theory for inflation to explain the homogeneity and isotropy of the universe and the origin of perturbation. We will be still scratching our heads about all the uncanny cosmological coincidences, comparable amounts of baryons, dark matter, and dark energy, neutrinos, and the many other coincidences outlined in Mark Reese's book, just 6 numbers. And I found another 6, so to spook. Can we derive all these numbers and the fine structure constant and from string theory? So, Craig and Joshua, are these coincidences? Are they hints to some underlying aha theory we have yet to discover? Is it just a coincidence? And does Jerry really have the answer to what dark matter is?
Yeah, I think he's right that we will know what dark matter is. I hope so. And I think it's axions, but I'll just because I can't bet it. The numbers are fascinating, and so one of those, one is they call the wine out problem. So, the universe is starting to accelerate now just as we're showing up. And so, why should the properties of the physical vacuum have anything to do with the lifetimes of stars? It's just, so right now this is just a fine-tuned thing. So maybe in 42, by that time we have this, we have one theory graph. Maybe we will have an explanation for that from math as opposed to anthropic arguments. But the current thinking, if you ask string theorists, is that there's a multiverse and these things will never be explained, and it's just it's a gamble. Yeah, it's a video game.
Do you want to add any?
What
I have sort of a pessimistic and an optimistic view. The pessimistic view is, we could be in the situation in 2042 where we still have, 96% of the universe is dark. We have no clue what it is. And, you could imagine heading into, a regime where people start to give up because the precision gets to be sub 1% in all these parameters, and people say, okay, we still haven't seen dark matter, it's dark energy, it looks like cosmological constant. People eventually just give up. And my concern in that scenario is that sort of the dark universe will take on this sort of quasi-mystical religious air, and well, okay, they're just making all this stuff up, it's just this dark stuff, you can't see it. And, hundreds of years, right, it may just be seen as this kind of backward quasi-mystical thing that we have no way of probing. So that's the pessimistic view. I think the optimistic view with regard to anthropic reasoning is I always go back to the 1970s, where people like Stephen Hawking had an anthropic explanation for the flatness of the universe. And if we had taken that seriously, people like Alan Guth would never have thought of inflation, a physical explanation for why the universe is spatially flat. And so that's at least one example where I think sort of what I call the pessimism of anthropic reasoning, because it basically gives up on a physical explanation, turn out to be, we think, wrong. And so my hope is still that we will come up with physical as opposed to anthropic explanations for some of these things.
So that one has come full circle. The multiverse is built on inflation.
Yeah.
And that is still.
Yeah.
Multiverse was mentioned.
We're still back to
But we tried to knock it down, and it came back in the multiverse. Yeah. We have the next quote here is from Wendy. I'm going to let Wendy hear this.
So I'm hoping we don't have all of the answers today, and that we will find some unexpected and new things by 2042. Q theory will be the new quantum gravity theory, and it will not involve strings. Dark energy will have turned out to be an epicycle. There will be a rich family of detected dark matter particles. There will be a standard theory of cosmology, but it will not be simple lambda CDM. Primordial gravitational wave and neutrino astronomy will have rewritten the textbooks on the early universe, but independent 1% measurements of Hubble constant will still not have overlapping error bars. But I think it's both I look at this as optimistic. I really hope there are new things to be discovered, and I think, I take Josh's point and I agree with it, that the fact that there were predictions about the acoustic oscillation spectrum decades ago, and that measurements now can measure with less than percent precision the fluctuations in the temperature in the microwave background is spectacular. And the push to D modes and polarization measurements, and the opening up of gravitational wave astronomy, happening, which is partly because people here, we are still learning something. And I think at some point we reached an impasse, and that was, we understand why the universe was so close to flat, but not exactly equal to flat, and something had to give, and we didn't understand large-scale structure, we only had matter, et cetera, et cetera. But I don't know what the answer is. We don't have a quantum theory of gravity, and we haven't probed some of these places where there's still big unknowns. And the degeneracies in the acoustic oscillation spectrum, it's not as if we just take a computer and churn out numbers. We really do have to have a model from which other parameters are derived, which is why the Hubble constant still keeps rearing its head. It's one of those important parameters. So if you can make these measurements even more accurately, then you can break those degeneracies. But where that will lead us in 27 years, I'm hoping that there's something still new to be learned, and the history is such to suggest there will be. But maybe we got it all right now. I doubt it.
Okay. This is the last slide that I want to open for questions. I think for questions. This is from Abby Berry, who graduated a couple of years ago. Abby, that's right. Yeah, sorry, I made a similar mistake before that. Anyway, Abby Kreitz, graduate student, graduated a couple of years ago. I hope that science is a more diverse endeavor by 2042. I hope they're doing education and science in a slightly different way. such that a more diverse group of people are contributing to the body of knowledge about our universe. This might come in the form of more citizen science projects and younger people getting involved in research, or a strong push to hire professors and administrators that are from many different backgrounds, so that universities and research institutions have a different culture than the one we currently have. I like to think we're making progress. If you look back 25 years or longer, certainly there's more to make, and hopefully Chicago will lead in this. So at this point, let's open it up. We have time, not much, but a little time for questions for our esteemed panel from the audience. Any questions? Steve, Meyer?
So one of the things that strikes me is the difference between the past and the future. And that's not just chance. In the past, if you look at how we have moved forward, it's always been surprises, especially in cosmology. A long list of big surprises. Nobody really expected. I think expansion is the first one. Expansion is the first one. Being able to understand nuclear synthesis is another one. The fact that there was a CMB temperature is another one. The fact that anisotropic was expected to finally be found. I think it changed how we thought about where we were going. It gave us a scale for the size of things. Inflation, well, not inflation, I shouldn't use that, that's a model, but acceleration is another huge surprise. Those are the things that have shaped.
Dark matter.
Dark matter. Those are the things that shape, actually, dark matter in general, that even comes before nuclear synthesis. Those are the things that shaped where we are. And making these predictions is very, very difficult if you realize that you could get hit from a direction you don't expect at all.
Right. So the warning at the beginning of the session was predictions are hard, especially about the future. Any comments on that from the panel?
Just very quickly, yeah, so I obviously agree with that, and to me the most astonishing thing, really surprising, is that basically cosmic structures are global phenomena. I did not believe that in 1990, but COVID convinced me that it's true. It's an incredible thing.
I'll make one prediction, that at the next meeting, there'll be more diversity than we're actually anticipating, that there will be artificial intelligence participating in this whole endeavor, and that if we're going to be talking about new language, we better start thinking now as to how to engage artificial intelligence and computers, both in the search and in the analysis and in the understanding. They may have insights that we are currently capable of, but we better figure out how to engage them and understand their solutions.
Any comments on the role of artificial intelligence? Stumped the panel. Very good, very good. Rick in the back.
I'll ask the panel, what technological leap do you think will have the biggest impact in the next 15 years? And it's a two-part question. The technological leap that you dream about, probably won't happen, and then the more realistic technological leap that you think might actually happen.
Leaps and bounds, anyone?
Gravity waves from space.
Gravity waves?
Pathfinder launches at December 2nd.
Neutrinos? Neutrinos, tritium decay, neutrino detectors? Computing?
Yeah.
From the audience? One last question, we're now running late. Okay, Carlo, last question.
So there's a link between fundamental physics and cosmology, obviously. But the way it's been discussed here today has been mostly in one direction, which is we'd like new input from the physicists. We'd like them to get their house in order so that we can know what to look for. I wonder whether you could talk about the leap running in the opposite direction, which is to say, what input, where would you go look for something that would help with the formulation of quantum gravity theory, rather than waiting for quantum gravity theory to help us?
That joke, that is Craig written all over it.
I look in the laboratory and not in the universe.
Yeah, why don't you?
I'll come back this afternoon.
Okay, so the answer to your question comes back in the afternoon.
Okay. Well, thank you all very much. I want to take a few minutes to thank the panel, but also all the alumni who wrote in and have made the trip as well. Thank you all.